Okay, welcome to part 2 of lecture 6. I am going to now move into chapter 4 of the book. Chapter 4 is devoted to taking the components that we have now learned, the different ports, and assembling them into bond graphs. The process is that we typically take some kind of schematic that is typically associated with a particular domain, and then we rewrite that in terms of a bond graph or a portion of a bond graph for multi-domain systems. We are going to focus on electrical, hydraulic, and mechanical, both linear translation and rotational motion. So sort of 4 domains that we will go over and work out these system models for, and then we will combine them all to have multi-domain models. So we're going to start with electrical networks. So this is now into chapter 4. We are going to assemble and create our first bond graph. So chapter 4, system models, and we will start with electrical networks. So you're going to have to dust off your circuits class a bit to remember some of these pieces, but these are the first bond graphs that we will work through. Alright, so I'm going to draw a little circuit that should look familiar, or at least the components of should look familiar. Alright, so what do we have here? I am going to the left. This is a voltage source, that small circle. And then I'm going to have a resistor that I'll label R1 in this circuit, and a resistor labeled R2. This curly thing is an inductor, as we have mentioned, and I'll call that a linear inductor with coefficient L. And then this middle line, I forgot, I want to add a capacitor with coefficient C. Okay, and then the bottom symbol here is the ground, or the negative side of the circuit. You can imagine that the circle E could be supplied by a battery, or maybe it's you plug into the wall, whatever we got here, but 2 resistors, a capacitor, and an inductor. So we've got some basic circuit that has an R, a C, and an L, right? Those are 3 primary components that we find in electrical circuits. And we have talked about these too. These are going to be associated with inertia, resistance, and capacitance ports. Okay, and the E, the applied voltage, will be associated with a effort source, right? And the ground here too, to think about that is, if I were to have an electrical, a voltmeter, and I put the negative end, I could add the negative end on any portion of the circuit that the ground has the same voltage as, and I could place the positive end of that multimeter anywhere else in the circuit to measure the voltage, right? I have to measure the voltages in the circuit relative to another voltage in the circuit, right? And that is typically taken as this some portion of the circuit that we call the ground, that I use as a reference. So I'll just note that this is going to be the reference voltage for determining the voltages at other nodes. Right. So, let me just label some of these things so you have them there, right? We're going to have, these are linear resistors. And then we've got the linear inductor. Linear capacitor. And a voltage source that can potentially vary with time. So I have that as a function of time. So here's a basic circuit that is written in standard schematic notation for an electrical circuit, and we want to develop a bond graph for this. So there is a basic 4-step process with a 5th optional step that will get us to a functional bond graph. So let's write down these steps. Right, for the first step, we are going to assign a power sign convention. We need to know what positive and negative mean in terms of power exchange among the components in this system. Step 2 is we're going to add 0 junctions or 0 ports for each electrical node, right, location on the circuit that have common voltages. All right, so now we have our 0 junctions. Step 3 is we will establish voltage drops across components using 1 junctions. Okay, and if we recall, a 1 junction is a summation of efforts, right? So we will be able to do some sums and minuses of to establish these voltage drops there. All right, so step 4 is the last necessary step. We're going to choose a ground or reference voltage, okay, node, and remove it. And we call these 0 power nodes, and I'll explain that when we actually do this. So we choose somewhere on the circuit to be our reference, and then we're going to remove the bonds that are associated with that, as we will assume that there are 0 power flow through that. And then the optional 5th step, it's generally nice to do this because you can make a tidy graph, is to simplify the bond graph. And there are some simplification rules that we will show you. Simplify. Alright, those are the steps. Assign a power convention, put 0 junctions for each voltage, establish voltage drops between those 0 junctions using 1 junctions, and then choose a ground reference voltage node, remove it, and it's all its associated nodes, and then simplify if possible. All right. So one thing I want to note too before we start is that the the 0 and 1 junctions enforce two of Kirchhoff's laws. If you dig back into your electrical introduction to circuits class, you should know that there is a Kirchhoff's voltage law, and this tells us that the voltage around a closed loop must be 0. Right? So this is associated with summations of the efforts or the voltages that we want to ensure that this law holds, and the 0 junctions will do that for us. And then similarly, Kirchhoff's current law is that the sum of the currents at junctions must be 0. Right, so at every 0 junction, we will sum the currents and ensure that those are 0. And I may have said incorrectly, the 1 junction is going to associate with the voltage law, which will let us sum the voltages. All right. So let's look at our circuit and let's see if we can apply these 4 steps. So I'm going to come up here and grab this we can reuse it. All right, so this is the circuit we have. Our first step is to assign a power convention. All right, so we're going to be establishing voltage drops across each of these pieces. I am going to start by adding a label to each node that is going to have a unique voltage. So I'm going to call this one A, B, D, F, G, H. Okay. So if I identify these sort of unique nodes in between the components, I'll just give them a label so that'll help us see what's matching up in the bond graph as we start to draw it. And we need sign conventions both for the voltages and the currents. So for example, on this voltage source, I am going to add a plus and a minus on each side of this to tell me what is positive voltage, what is a positive or negative voltage drop. And then I am going to draw a current, a little arrow here that says current flow in that direction is positive. So I am setting up for the current flow, like if there is current from the bottom to the top across that E, I'm going to call that a positive current. So I'm just establishing that sign convention for current. And for the same thing, the plus and minus to the left establish the sign convention for the voltage. And it means that if I move from the bottom to the top, I will have a gain in voltage, and that will be a positive value. Right. So I want to look at each component, and I'm going to do the same thing. For these, I'm going to say for the resistance, we'll have a current flow that's positive in that direction, but that I will see a drop in voltage. Right? So I'm going to establish that across that resistor, if there's a drop in voltage, that will be a positive power flow. associated with that current. And then I'm going to do the same thing for each of the other components. So I'm establishing that current flow through that component in the direction drawn, and a drop in voltage across that component will give me positive power. Right. So I've got my components there. I've labeled now a sign convention for both the effort and the flow variables for each of these components. So that is step one. Okay. If we don't have a sign convention, we won't know how to draw the half arrows when we set up our junctions. All right, so we're good to go over here in our schematic. Now we can start to develop the bond graph. Step 2 is to add a zero junction for each electrical node that has common voltages. Right? So I've got A, B, D, F, G, and H labeled. I am going to add a zero junction for each of those. And I'll transfer the letters over so that we know what's what. Right. So I have a zero junction for each node of this circuit, and that is tied to an effort at that node. We know that the zero junctions are common efforts, so I have a common voltage at each of these nodes, and we can move on to step 3. Step 3 is to establish voltage drops across components with one junctions. All right. So let's look at between A and B. We have a resistor that it will cause a voltage drop across that resistance R1. So I'm going to add a 1 that will establish a voltage drop between A and B that's associated with this resistance R1. Right? So I'm always, by convention, going to draw the half arrow towards the R. Right? And then, following my sign convention that I established in the schematic, we want to make sure the summations, so I have effort at A and effort at B, okay, and then flow is all the same here, so this is flow between A and B, right? They are in common one junction, so I can note those down. I want to ensure that we see a voltage drop here for my sign convention, and that would mean that we want EA, the voltage on the A side, minus the lower voltage on the B side to give us a positive value. So I want this to be EA minus EB. And to do so, for a one junction and the summations to work out, I would then put my half arrows like so. So this ensures that the effort on the bond attached to the R is EA minus EB, and that would give me a positive voltage if EB is a smaller value than EA. Okay, so then I have a positive voltage drop value and a positive flow, and I should have wrote current there, I guess let me change those to I's, right, a common I, and then I get a positive power into the R if there is a voltage drop across that R. So this establishes power flow positive into the R means we will dissipate energy, and it's tied to this voltage drop that we've established with the one junction. Right? And I took time and wrote each of the efforts and flows on the bonds to think carefully and make sure that I've sort of set up those sign conventions properly. So similarly, I can do the same thing between B and D, and I have the same sign convention written. So this should be pretty straightforward there. I have a voltage drop, that then this one is EB minus ED. and then a common flow there to that resistance. I can go through for each other component and have these same setups. So this is an inertia port. It has a linear coefficient L. Right? And then we have a capacitor here. Yeah. Now between F and G and H, there is no component. So I can simply add a bond that connects those two. Right? And that means that F, G, and H, in fact, all have the same voltage. Right? There's no one junctions in between them, so we don't have any changes to the voltage. And the last one here is I've got a effort source. So an effort source is going to draw that above there. E of t. We've got this effort source, and we want to establish that's a power convention that's written slightly different, right? I have the with respect to the current flow, right? If I have positive current flow, then I want to have an increase in voltage from H to A. So I'm going to set up a positive power into the circuit here from the E, and if this is EH and EA, I want the a positive summation for the EH and EA to be positive if EA is a larger number than EH. So to do so, I can put my half arrows like so, and that means that I will. This is going to then be that EA minus EH, right? So our one junction there is EA, left and right. EA, it has a sign away from the one, minus EH, minus whatever the voltage is at the SE. So I'll call that ESE equals 0. And then I can see that EA minus EH equals ESE. Right? So that fits the one junction. I have the proper sign convention. And if EA is a larger number than EH, I have positive power flow into the system. So you want to double check that these summations do have the right signs and you set up the arrows appropriately. All right, so that completes step 3. I have here established all my zero junctions, and then for each component I have these voltage drops associated with the one junctions. I've written my ports, labeled them, and made sure my sign conventions are correct with my half arrows and that things add up as expected. Step 4 is to choose a ground node or a reference voltage node and remove all associated nodes that thus would have zero power. Right? So I already said that the ground is would be a good choice would be the ground at G. We can actually pick any node we want to call the ground. It could be A, B, D, H, G, F. It's all equivalent, but if I choose G, I'm going to get to eliminate H, G, and F from my bond graph, and it'll be a little simpler than if I didn't choose those. So I am going to select G as my ground node, right? And this means that we are going to say that that is the reference voltage, and that voltage is 0. If voltage is 0, well, voltage times the current is also 0. Power is 0. So we can then eliminate that junction G. All right. If I eliminate G, well, G is the same as F, the same as H. I am going to get to take this whole chunk and eliminate it as my reference voltage nodes, right? So H, G, and F, they're the same voltage, they're the same reference. I am eliminating them as the ground. Right? This ground voltage or reference voltage that I would measure the other voltages with respect to. Okay, so I eliminate that. And the last step, step 5, we can do is to simplify this. So I'm going to write this a little easier. And one of the simplification rules that we can use right here, the first is that if I have a 1 or a 0 junction, that only has 2 ports, then I can just replace those with a single bond. So if I have a 2-port 0, 1, I can replace those with a single bond. And I'm going to see a couple here once I stretch this out between the SE and the A. Actually, between SE and the 1 junction with the R1, those are 2 1s and 0s that only have 2 ports. I'll be able to eliminate those. So to finalize this bond graph, I can write SE, and this is going to go then straight to the 1, right? I'll have my R1, and then I need to retain this 0 junction because it has 3, but I can get rid of the 1 junction between the B node and the capacitance for simplification. Oh, I wrote that in the wrong spot. So that's that. And then I have another resistance. And that resistance has 2 2-port nodes there, so I can go straight to the I on the end. There we have it. This is a simplified final bond graph for that circuit. And I see all the elements. I have the 2 resistances, the capacitor, and the inertia. And I have the voltage source. These 1s and 0s ensure that Kirchhoff's voltage and current laws are correct for the associated circuit. That is your first bond graph. Okay, so I will end this here, and then when we come back to lecture, when I return, we will work on some exercises and try to do some more of these electrical circuits. Right? And that'll probably take up most of the next class. But that's your first bond graph. There's 4 steps and 1/5 optional. As you're learning bond graphs, you want to follow these steps specifically. Okay, don't try to jump to the end, even if you think you know how this bond graph is going to end up. Do all the steps. Once you establish following the steps and know that you can get the correct answer, you will start to see what the bond graphs are going to look like in the end, and you can skip steps. But don't skip any steps as we start. All right. So we'll call that, and I will see you all when I return.